Welcome to a journey beyond Newton and Einstein, a new vision of gravity that breathes with the universe itself. In this series, we introduce Casimir-Flow Gravitation, CFG, a theory where vacuum energy flows shape mass, time, and cosmic structure. Unlike traditional gravity, CFG proposes that a directional energy current, the Casimir flow, slows forward time and accumulates matter. This is not just a tweak to existing ideas, but a bold new paradigm that could explain mysteries from cosmic expansion to the very nature of mass. Let's embark on this exploration of mass, time, and the universe's hidden currents. Gravity's story began with Newton's force and evolved with Einstein's spacetime curvature, but neither fully explains why heavier elements clump together, why time slows near mass, or what moderates cosmic expansion. Casimir-Flow Gravitation steps in with a fresh answer. Gravity is not just a force or a curve, but a flow, a macroscopic, time-directed vacuum energy stream that gathers mass and drags time itself. Imagine a glowing cone, its plasma-like lines pulling matter inward, shaping the universe in ways we're only beginning to understand. The heart of CFG is the Casimir flow, a large-scale directional vacuum energy gradient. Unlike the spacetime curvature of general relativity, this flow exerts a net inward influence, modulating local time and inertia while accumulating mass. Think of it as a cosmic river, with currents that slow time for anything caught in their path. The stronger the flow, the slower time moves, and the more mass gathers. This is the engine that powers the universe's structure, from galaxies to atoms. One of CFG's key predictions is forward time drag. As matter moves through the Casimir flow, its proper time slows compared to the vacuum far away. The effect is stronger for heavier, hotter elements. Hydrogen barely feels it, but gold or uranium experience significant time drag. This means that the universe's densest regions are not just heavier, they're slower, their clocks ticking at a different pace. This time drag is measurable and could explain why dense objects behave the way they do. CFG introduces a two-layered gravity, the primary Casimir flow that accumulates mass, and a secondary classical gravity that tethers it. Picture a glowing cone of energy Casimir flow overlaying a soft, golden grid classical gravity. Mass floats in the balance, suspended between these two forces. The Casimir flow does the heavy lifting, gathering matter, while classical gravity gently binds it together. This dual structure explains why gravity behaves differently at different scales. CFG, there are special regions called neutral zones, temporal isosurfaces where forward time and negative energy backflow perfectly balance. Here, time nearly stops. At the tip of the Casimir cone, matter can enter these zones, experiencing a profound slowdown. These are not just theoretical curiosities. They could exist near black holes or in engineered lab setups. Neutral zones are the gateway to some of CFG's most exotic predictions. The very tip of the Casimir cone, something remarkable can happen: quantum threading. Here, matter can tunnel through the neutral zone, transitioning into negative energy states. This is a non-perturbative quantum event, rare but possible. It offers a new perspective on black hole interiors, singularity avoidance, and the potential for exotic astrophysical phenomena. CFG predicts that under the right conditions, positive mass states can neutralize and re-emerge as negative energy matter. CFG is built on a rigorous mathematical framework. The key fields are the metric spacetime geometry, the flow potential Casimir bias, and the flow vector vacuum energy current. Matter couples to the flow through a tensor that depends on density, temperature, and atomic number. The action and field equations extend Einstein, adding terms for flow dynamics, matter coupling, and back reaction. These equations predict how mass, time, and energy interact in the presence of Casimir flow. CFG predicts a precise law for time dilation. The local rate of proper time slows exponentially with the strength of the Casimir flow. The drag parameter increases with atomic number and temperature, so heavier, hotter matter experiences greater time slowing. This law can be tested with atomic clocks and explains why dense, hot regions of the universe evolve differently from diffuse, cold ones. As the Casimir flow intensifies, not only does time slow, but effective inertia and weight increase. The theory predicts that objects in strong flow fields become harder to move and feel heavier. This aligns with observed density trends at large scales and offers a new explanation for why massive bodies resist acceleration. It's a subtle but profound shift in how we understand mass and gravity. Casimir flow is not uniform. It focuses into cone-like structures, funneling vacuum bias into mass-rich regions. At the cone's tip, the flow is strongest, and neutral zones can form. This cone geometry is central to how CFG accumulates matter and creates the conditions for quantum threading. It's a visual and conceptual leap from the smooth curves of Einstein's spacetime. CFG predicts that the Casimir flow couples differently to different elements. Hydrogen, with its low atomic number, barely interacts and streams freely with cosmic expansion. Heavier elements, like gold or uranium, experience much stronger time drag, higher effective inertia, and greater density. This explains why the universe's densest regions are rich in heavy elements and why mass clusters as it does. One of CFG's most exciting implications is its effect on cosmic expansion. The Casimir flow provides a scale-dependent break, slowing expansion without forcing collapse. This offers a new explanation for dark energy. Instead of a mysterious repulsive force, cosmic acceleration is moderated by the drag of vacuum energy flow. This prediction can be tested by looking for subtle red tilts in large-scale velocity fields. FG describes a two-stage process for forming stars and planets. First, the Casimir flow aggregates interstellar material along cone structures, concentrating mass. Then secondary gravity compresses and heats this material, triggering thermodynamic and nuclear reactions. This dual mechanism explains why stars and planets form where they do and why their properties depend on local flow conditions. FG predicts that neutral zones can form outside classical black hole horizons, creating pockets where time nearly halts. In these regions, rare quantum threading events could seed negative energy shells or jets, altering the energetics near black holes. This offers a new way to avoid singularities and may explain some of the universe's most energetic phenomena. FG is not just theoretical, it makes concrete predictions for laboratory experiments. Heavy element atomic clocks placed in structured vacuum cavities should show extra time slowing beyond what general relativity predicts. Tailored micro and nano cavities could generate measurable mass renormalization, and dense materials should show apparent weight increases in strong flow fields. These effects are within reach of current technology. FG predicts that regions rich in heavy elements will show enhanced clumping and slower local time compared to hydrogen-dominated clouds. Near compact objects, transient time-neutral layers should cause phase delays in emissions, effects not explained by general relativity. On the largest scales, a mild red tilt in velocity fields should correlate with Casimir flow gradients. These are all testable with modern astrophysical surveys. FG stands apart from Newtonian gravity, which sees gravity as a force, and Einstein's general relativity, which sees it as curvature. It also differs from quantum gravity approaches that struggle to unify vacuum energy with cosmic structure. CFG's unique contribution is to tie vacuum energy flow directly to mass accumulation and time drag, offering a unified framework that addresses density scaling, expansion moderation, and singularity avoidance. Key strength of CFG is its testability. It predicts measurable anomalies in atomic clock drifts, weight scaling, and astrophysical timing lags. It also offers a path to unify quantum vacuum effects with macroscopic gravity, something no existing theory fully achieves. By resolving the cosmological constant problem and offering alternatives to singularities, CFG positions itself as a true successor to previous gravity theories. CFG is more than a theory. It's a new chapter in humanity's understanding of mass, time, and the universe. By bridging quantum vacuum dynamics with cosmic structure formation, it offers a unified vision that could guide future research for decades to come. Its predictions are bold, its mathematics rigorous, and its implications profound. The journey from Newton to Einstein to CFG marks the evolution of our deepest scientific ideas. Casimir-Flow Gravitation invites us to see the universe as a living, breathing entity where time slows, mass gathers, and vacuum energy flows shape everything from atoms to galaxies. As we test its predictions and refine its mathematics, CFG may become the foundation for a new era in physics. The universe, it turns out, is not just curved or forced, it flows. And in that flow, we may find answers to the deepest mysteries of existence.